Welcome to KMI's headquarters, the Castle of Wolfsberg, in Carinthia in the south of Austria. My name is Michael Kleiner. I am the responsible sales manager of KMI. Today I would like to give you some information about our company, and afterwards I will give you a technical presentation about our products and their applications. KMI is a family-owned company. It was founded in the year of 1932, but the mining operation is already possessed by the family since 1851. KMI is the world market leader in the micaceous iron oxide business. We are very export orientated, so the export rate is more than 95% in more than 80 countries worldwide. We have a strong focus on grade A quality products. Beside our own raw material resource, we use several raw material resources all over the world to have a secured supply, especially for grade A qualities. Beside that, we are also experts in micronization and delamination of products, and we are the acknowledged R&D leader in the field of micaceous iron oxide products. Additionally to the micaceous iron oxide products, we also produce industrial minerals like micas, wollastonite and talc products. Few words about the application fields. We sell our products to the coatings industry, to ceramics, to friction application, in polymers, in foundry industry and also in building materials. Today I'm going to speak about micaceous iron oxides as functional minerals in coatings, and especially about the potential of micronized grades and their new applications. At the beginning, I would like to speak about a few basic properties of micaceous iron oxide. Micaceous iron oxides are functional minerals. You can say they are a green product, a natural product out of an underground mine, just mechanically treated, so no chemical treatment. That means there is no REACH registration necessary. The product itself is foot contact approved. There is no crystalline silica inside, so you can handle the product pretty much without any limitation. From the mineralogical point of view, it's hematite. The chemical formula is Fa2O3, which is the highest oxidation step of iron, which is the most stable form at ambient atmosphere. The particle shape is the biggest difference to all the other iron oxides on the market. The particle shape is platy, like mica. This is the reason why the product is called micaceous iron oxide. The color is dark gray to reddish brown, depending on the particle size distribution, and the density and the hardness are typical values with iron oxide. So the density is almost 5 grams per cubic centimeter, and the hardness is in between 6 and 6.5 moles. There is an international standard just dealing with the quality of micaceous iron oxide. It's the ISO 10601, and beside this standard there are a number of national regulatories available, also dealing with the quality of MAO, which has to be used for certain kinds of coatings. For example, in Germany it's DBTL core. The most important quality criteria of micaceous iron oxide is the content of lamellar particles, which has to be minimum 65% according to the ISO standard. Then you need a constant color, which should be gray with a metallic sheen. And also the Fa2O3 content is defined with a minimum of 85%. Now, what is the effect of MAO in coatings? The first effect is the so-called barrier effect. Due to the fact that micaceous iron oxide is a platy mineral, it is able to build up a barrier layer in coatings which simply make diffusion ways down to the substrate longer. On the examples here on the left hand side you see a picture where you have a mixture of granules and lamellar particles, and you can see it's not possible to get a good barrier layer or barrier effect here on the left hand side example, and on the right hand side you can see a product predominantly consisting of platelets, and it's in a good position to build up a very dense barrier layer to protect the substrate. When you look at the mineral itself, not only the shape is important, also the crystal lattice is important. For example, if you compare a mica particle with a miox particle, there's a big difference. When you look at the mica particle, it's only a two-dimensional stable crystal lattice. That means you have strong bondings within the layer but weak van der Waals bondings in between the layers. So if you have, let's say, an attack of a salt solution in a coating, the salt solution can penetrate the space in between the layers and can crack the particle. When you look at the micaceous iron oxide, this is the picture on the bottom of the right hand side. It's a three-dimensional stable particle, so there's no space to penetrate, and it's a very chemically resistant mineral. The outcome of this you can see on these two test panels. This is previous clean steel with a single layer 2K epoxy coating. It's solvent based. On the left hand side we formulated with mica as a filler, and on the right hand side we formulated with Miox at the same pigment volume concentration, and we put the panels in a salt spray test, and you can easily see the difference. So there is a lot more of blistering because of cracked mica particles, and a lot more of delamination and rusting around the scribe compared to the right hand side picture where you have the Miox as a passive anti-corrosive pigment in the formulation. The next effect of MAO is the so-called shield effect. What you can see here is we measured the transmission rate on a polypropylene filled film. We produced a 200 microns thick film. One film was filled with talcum powder just to compare, and the other film was filled with Miox, again at the same pigment volume concentration, and we measured the transmission rate over the whole spectra. And what you can see here, there's a steadily increase of the transmission rate with the talc filled film, and it's almost a baseline, so no transmission with the Miox filled film. That means Miox is an exceptional radiation absorber and reflector. This is a very useful feature, especially when you work with UV sensitive resins like epoxies. Miox in this case is really in a good position to prevent the resin against degradation. So this is also a good thing, using Miox in top coats as a radiation shielder. The third effect of MAO is the improvement of adhesion. That means the improvement of adhesion on substrates, but also the intercoat adhesion. What you can see here are three test panels. The substrate is galvanized steel, so hard to coat. On the left hand side you can see a 2K epoxy filled with mixture of talc and dolomite, which is a typical filler material. In the center you can see again a 2K epoxy with MAO standard grade, and on the right hand side you can see again 2K epoxy filled with a MAO micronized grade, again at the same pigment volume concentration. We did the pull-off test, and what you can see here, with the talc dolomite mixture you have 100% failure between substrate and coating. With the MAO standard you already have 80% adhesion and only 20% failure, already a big improvement. And with the new micronized grade you have 100% adhesion between substrate and coating, which is really a remarkable improvement. So if you have issues with adhesion on difficult to coat surfaces or problems with the intercoat adhesion, Miox is really in a position to improve these adhesion problems. Now a few words about the available grades. I would like to start with the standard grades. These are the old grades developed around 1900. There are three different grades available. All the grades have a top cut of 100 microns, so that means the products are sieved, easily sprayable, also airless sprayable, and the sieve residue at 63 microns is roughly 10%. What is the application of these standard grades? It's mainly protective coatings, and there it's used for heavy duty anti-corrosive coatings, so more or less for every steel structure outside, like drilling platforms, bridges, other infrastructural equipment made of steel. And beside that there is also an application which is called decorative metal protection. With the micaceous iron oxide you can create nicely looking hammered iron, cast iron effects. This is a very popular application, especially in the south of Europe like Spain or Italy. When you walk there around and you look for garden fences, street lights and so on, and it looks like old hammered iron, cast iron. It is a simple steel structure coated with an MAO loaded coat with quite high loading levels. And due to these high loading levels, beside the decorative effect, you also get a protection effect. But there is a limitation of the usage of standard grades, mainly due to the quite coarse particle size distribution. That means there is a minimum dry film thickness of not less than 60 to 70 microns to get a good corrosion protection when you use standard grades. And this was the reason for us to start a development to develop some new micronized grades, and the technical challenge was to find the right grinding equipment to keep the lamellar structure and keep the functionality of the coating. That means keeping a high aspect ratio, also having a steep particle size distribution, to have most of the product in the so-called working window, and also to keep the color gray with a metallic sheen. And finally, we have been successful and we developed a series of new called micronized and sub-micronized micaceous iron oxide products. Now when you look at the grades, we start with a micro 50, which is the coarsest micronized grades, down to the finest one, which is called sub-micro 2.5. It's easily to read. The name of the micronized grade is always the D98 of the particle size distribution. So that means, for example, when you look at the micro 30, the D98 of the particle size distribution is 30 microns. When you look at the color itself, the products are gray with a metallic sheen down to the micro 30, and from the micro 20 on to the finer grades, it turns more and more into red. The reason for that is the following. Micaceous iron oxide is gray with a metallic sheen, but the original color of the product, of the mineral, which is hematite, is reddish, and we found out that when you grind the micaceous iron oxide products below 5 microns, the color switches from gray into red. So that means what we do for the gray grades, we grind the products and we classify as a last processing step the ultrafines out to come back to the gray color. This is possible down to the micro 30, which is the finest gray one, but doesn't make sense from an economical point of view for the finer grades. So there we leave the reddish particles, the fine particles in, and the product turns more and more into red. Now a few words about the test work we perform in our lab. For single layer coatings where we test just the barrier properties, we use the typical salt spray test according to ISO 9227. And for coating systems or multi-layer coatings, we prefer to use so-called combined cyclic weathering and corrosion test according to ISO 2340. This is a 7-day cycle, as you can see here in the picture, which has 3 days QV testing, alternating every 8 hours. Then you have the typical salt spray test for another 3 days, and then you have a low temperature exposure at minus 20 degrees C for 1 day, and then you start the cycle again for 25 cycles, 25 weeks, which means it's a 6-month test, which is a quite harsh test developed for mainly harsh marine environments. A few words about the test setup, the systems and formulations we used. We always tested the 2 and 3 layer systems with dry film thicknesses per coat in between 50 and 100 microns. The substrate was always steel, sometimes previous cleaned, but also sandblasted or galvanized. We always had a 2K epoxy zinc phosphate primer, which is a typical on the market available product. Then we had a 2K epoxy MAO coat where we played around, and optionally we also had a 2K polyurethane top coat in the test series, and all of them had been solvent based. The standard formulations had been developed according to the DBTL 918300, which is a very well known standard for infrastructure and railway equipment in Germany, because DB stands for Deutsche Bahn, which means German Railway. A few words about the micaceous iron oxide products we tested. We tested our standard grade Mioxis G, which has a content of lamellar particles of 80%, which is the most crucial quality criteria regarding the performance. Then we tested an experimental product with the same particle size distribution, but only 10% lamellas. That means it's more or less a granular iron oxide, which you can also find on the market, sold as micaceous iron oxide. And the third one is one of the new grades, the Miox Micro 30, which is roughly 3 times finer than the standard grades, and the content of platelets or lamellas is also 80%. Now to the test results. What you can see here are the test panels after this 25 weeks combined corrosion and weathering cycle. Here you can see the 2-layer systems, so you have a 2K zinc phosphate as a primer and the 2K epoxy on the top. The only difference between these two test panels here is the quality of MAO. On the left hand side you can see the standard grade with only 10% of platelets, and on the right hand side you can see the standard grade with 80% of lamellas, which is our Myox SG grade. And there is a big difference in the performance. What you can see here on the left hand side, there is a lot more of film degradation and delamination and rusting around the scribe compared to the right hand side picture, where you have almost no film degradation and also a very stable situation around the scribe. The reason for that shows the following model. So when you work with a more granular micaceous iron oxide product and you have UV radiation on your coating, then you have the following effect: that due to the film degradation you will lose the first layer of coating of polymer, then the granules will begin to stick out of the coating, and as a last step the granules will break out of the coating. You create pinholes, the UV radiation can enter these pinholes and the degradation goes on and on. When you compare it with a more lamellar type of micaceous iron oxide, you will see the same effect at the beginning, so you will lose the first layer of resin in between the platelets. But due to the fact that you have platelets and you have still a good adhesion on the resin, you will end up finally with a layer of micaceous iron oxide platelets overlapping on the top, absorbing and reflecting every kind of radiation and protecting the resin against degradation. The next test is a comparison of this high lamellar standard grade versus the high lamellar micronized grade on the right hand side, and what you can see here, it's another improvement of the performance, especially around the scribe. That means delamination and rusting around the scribe is less than with the standard grades. So that means the micronized grades outperform the standard grades. With the results of the first test series that the micronized grades outperform the standard grades, we set up a new test series where we again tested 2 and 3 layer system, again a prime coat with zinc phosphate with a dry film thickness of 60 microns as a prime coat. Then the second coat, there we had 3 different formulations. A formulation A was filled with standard micaceous iron oxide with a loading level of 40% per mass and a dry film thickness of 100 microns. The formulation again to this DBTL guideline. Then we had a formulation B where we replaced the standard grade with micronized grades, but with a loading level of only 24% instead of 40% with the same dry film thickness of 100 microns, and the missing MAO was partially substituted by a micronized talc grade to keep the PVC constant. And we had a formulation C we filled with micronized micaceous iron oxide at the same loading level, so that means 40%, but we cut back the dry film thickness from 100 microns down to 50 microns. And optional, we tested the third coat, which was a typical polyurethane top coat with again a dry film thickness of 160 microns. And optional, we tested the third polyurethane top coat, which is a typical top coat with a dry film thickness of again 60 microns. Here you can see the test results. We tested blistering, rusting and delamination around the scratch. Again, after this 25 weeks cyclic corrosion and weathering test. Formulation A, just to remember, is the standard. Formulation B is with a lower loading level of micronized MAOs, and formulation C is the same loading level but a thinner film for the MAO based coating. And you can see the test results are absolutely comparable. That means blistering, rusting and delamination are more or less similar. That means as an outcome of this test series, you can reduce the necessary amount of MAO almost down to 50% and you get the same performance compared to the standard grade, and you can cut back the dry film thickness of the coating by keeping the same performance. These test results led to a number of new application possibilities with the micronized grades, and all these applications are already commercialized. That means we have customers doing that. The first new application is the usage of micaceous iron oxide products in water-based anti-corrosive coatings. If you want to formulate water-based and you want to work with standard grades, you immediately run into troubles because the product itself is quite coarse. You need a high loading level, and due to the high density, you always have rheological problems like settling rates and so on and so on. With the micronized grades, you have two advantages. The first is the micronized grades is approximately 3 times finer than the standard grades, so that means you have much lower settling rate. And the other advantage is you can reduce the necessary amount of MAO down to 50%. So it's much easier to stabilize. You have much more freedom in your formulation around. And you have a lower influence on color and gloss. Another application is the partial replacement of zinc dust in zinc-rich prime coatings. The Corrosion Institute in Dresden and we found out that the partial replacement of up to 50% per mass in a 1-to-1 ratio is possible. The advantages are you have environmental advantages because you can lower the zinc content of your coating. You have some technical advantages. You reduce the building of zinc salts, which has a positive influence on the intercoat adhesion. And for sure you have again the effect of better adhesion, especially on difficult to coat surfaces. And last but not least, it's a money-saving solution in cases of high zinc prices, because micaceous iron oxide is a typical industrial mineral product, is traded as an industrial mineral product, which means the pricing is more or less constant with small adjustments more or less to the inflation rates. And on the other hand, zinc dust is traded on a metal exchange and the pricing is much more volatile compared to micaceous iron oxide. So especially in case of high zinc prices, it's a good alternative to use micaceous iron oxide. When you look at the test panels on the right hand side, these are test panels of one of our Italian-based customers doing an aerosol spray can zinc-rich coating. The left panel shows his standard formulation with a zinc loading level of roughly 60%. On the right hand side, it's the new formulation with zinc MAO, where he replaced 50% of the zinc with the micaceous iron oxide grade Miox Micro 40. And you can see there is no difference in the performance after doing a salt spray test. The latest results we have on this application is that a replacement rate of up to 50% is possible to get similar performance, but we also found out that at loading levels of around 10% you can really improve the performance of an existing prime coat. Here you can see a typical base formulation. It's a 2K ethyl silicate zinc MAO primer. And here you can see we have a replacement rate of roughly 30%. So we have 27% of Miox Micro 40 in the formulation and still 45% of zinc dust, which is a typical starting point. Another application is a simple way to improve existing prime coatings simply by replacing a small amount of the filler with micronized MAO. Here we speak about 5% per mass up to maximum 10% per mass. It's an easy way to improve the anti-corrosive performance simply because you do not have to change your formulation around. So you can work with the same active pigment package, you can work with the same additives. There is just a slight influence on the color if you replace a white filler with a dark gray micaceous iron oxide. But here we speak about a prime coat and there shouldn't be a big issue with that. For sure it's a cost-performance ratio. If we replace this cheap filler with a more expensive micaceous iron oxide grade, but simply if there is a need and you look for an easy way to improve an existing prime coating, that's a good application. Micronized MAOs can also be used in heat-resistant anti-corrosive coatings. Here we speak about silicone-based coatings with working temperatures of up to 550 degrees C. The reason for that is micaceous iron oxide has a very high melting point of 1400 degrees C, so which is far away from any limits of the resins.
Micaceous iron oxide, although it's only a passive barrier pigment, when you use one of the finer micronized grades, for example micro 15 or micro 10, you can create quite reasonable corrosion protection without any active pigments, because there are the limitations. For example, the melting point of zinc dust is 420 degrees C. You can have some heat stabilized zinc dusts withstand a little bit higher temperature, but far away from 1400 degrees. And the application for these coatings is mainly industrial applications like mufflers in the automotive industry or in heat exchanging devices for calorific power plants. So in every area where you have humidity, you have corrosion and high temperatures, but it can also be used for barbecue grills. Last but not least, micaceous iron oxide can also be used in powder coatings. We already had applications for standard grade tints many years, but only for decorative effects. And due to the coarse particle size distribution, the possible loading level in the powder coating was simply too low to create anti-corrosive coatings. But now, with the micronized grades, you have two things working in the right way for you. The first is they are much more efficient. That means the necessary loading level to get a good corrosion protection is much lower. And on the other hand, they are much finer, so you can apply much more in your powder. So with the micaceous iron oxide micronized grades, now you're also in a good position to create good performing anti-corrosive coatings on powder base. So at the end of the presentation, I will make the following conclusions. Micaceous iron oxide is a typical functional mineral which really outperforms other lamellar minerals like micas, for example. The product quality, especially the content of laminar particles, is a crucial factor and decides about the coating's performance. And with the new micronized grades, there is no longer a limitation of the minimum dry film thickness. The necessary loading levels are lower, and this offers a range of new applications like coatings with improved anti-corrosive performance, partial replacement of zinc in prime coatings, water-based anti-corrosive coatings, thin film coatings, improved prime coatings, heat-resistant anti-corrosive coatings, and also powder coatings.
Thank you very much for your attention. If you need any additional technical information, or if you need a sample to play around with one of our products, please do not hesitate to contact us or one of our distribution partners in your home country. The contact information is available on our webpage www.kmi.at. So thank you very much for your attention. I wish you a nice day and goodbye.